All right, let's dive right into one of the biggest, most mind-bending concepts in all of physics, entropy. It's this hidden rule that secretly runs everything, from why your morning coffee gets cold to, believe it or not, the ultimate fate of the entire universe.
I mean, have you ever really stopped to think about it? You can scramble an egg, but you'll never see the scramble turn back into a perfect egg. A building might crumble over decades, but it's not going to spontaneously rebuild itself. It feels like time is a one-way street, right? But here's the weird part. The basic laws of physics, like the conservation of energy, they don't actually forbid these things from happening in reverse. So, what does? What's the law that makes time flow forwards? Well, the answer is a little thing called entropy.
So, we're going to kick things off by looking at these one-way processes, or what physicists call irreversible processes. They're so common, so baked into our reality that we barely even notice them. But they are the absolute key to understanding why time has a direction at all.
Yeah, these are all things you see every day, right? We just know that coffee cools down. It doesn't magically get hotter by sucking heat out of the air. We know that when a balloon pops, the air inside spreads out everywhere. It doesn't suddenly decide to gather itself back into the shape of a balloon. These are all irreversible processes, and every single one of them points in the direction that we call forward in time. And the scientific idea that explains this direction is entropy. Okay, so here's the absolute heart of the matter. For any irreversible process that happens in a closed system, and that just means nothing gets in or out, a property we call entropy will always increase. I mean it, always. It never, ever goes down. This unstoppable, relentless increase is what gives time its arrow. When a popcorn kernel explodes, that's entropy going up. If you ran a video of that backwards, you'd be watching entropy go down, and that's precisely why it just doesn't happen in the real world. Now, to really wrap our heads around what entropy is, it helps to think about it in terms of order and disorder. So let's dig into that with a classic physics thought experiment. It makes things a lot clearer. Okay, so picture a box. It's totally insulated from the rest of the world. Inside that box, we've got a bunch of gas molecules, but they're all penned up on the left side by a little wall. The right side is a complete vacuum. See how neat and tidy that is? Everything's in its place. That's a very ordered arrangement. In the language of physics, we call this a state of low entropy. So what do you think happens if we just, poof, remove that barrier? Well, you know exactly what happens. The gas molecules rush out and spread themselves evenly throughout the whole box. The system goes from being all ordered and neat to being completely disordered and spread out. That's a high entropy state. And this little experiment shows you the core idea perfectly. Systems, when left to their own devices, naturally move toward states of higher disorder, higher entropy. And you will never, ever walk back into that room and find that all those gas molecules have somehow decided to huddle back on the left side again. It just won't happen. The process is irreversible.
So how do scientists actually put a number on this change? They use this relationship. Now, I know, the formula looks a little intense, but the main idea is actually pretty straightforward. The change in entropy, that little triangle S, is related to the amount of heat that's transferred divided by the temperature. Now here's the catch. This formula is technically for a perfect, reversible process, one you can run forward and backward without losing any energy. Our gas expansion was messy and irreversible. But here is the genius trick. Because entropy only cares about where you start and where you end up, physicists can just imagine a perfect reversible path between those same 2 points to do the math. It's a clever mathematical workaround that lets them calculate the entropy change for real-world, messy processes.
Okay, so this might all seem a little out there, a bit abstract, right? But entropy has some incredibly real, practical consequences. In fact, it's the very reason we can't build a perfect engine, a machine that could turn heat into work with 100% efficiency. So let's take a look at how entropy puts a hard, unmovable limit on our technology. You know, every heat engine out there, whether it's the one in your car or a giant one in a power plant, works on this exact same principle. First, it takes in heat, we'll call it Q sub H, from something hot, like burning fuel, at a high temperature, T sub H. Then, it uses some of that energy to do useful work, W, like turning wheels. And finally, and this is the absolute key part that entropy demands, it has no choice but to, discard some leftover waste heat, Q sub L, into a cold place, like the air around it, at a low temperature, T sub L. There is just no way around it. To figure out the absolute best an engine could possibly do, we have to look at a perfect, idealized engine called a Carnot engine. It runs in a 4-step cycle. First, it expands at a constant high temperature while it soaks up heat. Then it expands some more, but this time without any heat getting in or out, which makes it cool down. Third, it gets compressed at a constant low temperature, pushing out waste heat. And finally, it's compressed again without heat transfer, which brings it right back to its starting point, ready to go again. The end result of this whole cycle is that some heat got turned into useful work.
This statement right here, this is one of the most important ways of stating the second law of thermodynamics. It's really just a formal, scientific way of saying what we've been talking about. Perfect engines are impossible. You can't just build a box that sucks in heat and spits out nothing but work. You have to pay a tax to the universe, and that tax comes in the form of waste heat that you've got to dump somewhere cold. It's a fundamental law and you can't break it.
So if a 100% efficient engine is impossible, then how good can we actually get? Well, the laws of entropy give us a very precise answer, and it turns out it all comes down to temperature.
This little formula is so elegant but so powerful. It tells us the maximum possible efficiency of any engine, and look what it depends on. Just the absolute temperatures of the hot source, TH, and the cold sink, TL. That's it. So if you want to make your engine more efficient, you need to make the hot part as hot as possible and the cold part as cold as possible. You want the biggest difference you can get. But even then, you can only get to 100% efficiency if your cold sink is at absolute zero, which is, well, it's physically impossible to reach. So this formula is basically the ultimate speed limit for any engine we could ever build.
So how does this perfect theory stack up against the real world? Well, the engine in a typical car, it only manages to turn about 25% of the energy from burning gasoline into useful work that actually moves you down the road. The other 75%? Yeah, that just gets dumped into the environment as waste heat, mostly out of your radiator and your exhaust pipe. It's a pretty sobering dose of reality, all thanks to the second law of thermodynamics.
And this really puts the scale of the problem into perspective. Just look at this nuclear power plant. To generate 900 megawatts of electricity for our homes, it has to throw away more than double that amount, a staggering 2,100 megawatts of energy as waste heat, just pouring it into the nearby river. And that's not because of bad design or sloppy engineering. It's a fundamental, non-negotiable consequence of the laws of entropy. That waste heat isn't a choice. It's a mandatory payment to the second law of thermodynamics.
And hey, just as a quick aside, it's pretty cool to realize that your refrigerator is basically just a heat engine running in reverse. An engine lets heat flow naturally from hot to cold to create work. A refrigerator uses work from its electric compressor to force heat to go the unnatural way, from the cold inside of your fridge to the warmer air in your kitchen. It's the same laws of entropy, just running backwards.
Okay, so far we've seen the what of entropy, that it's this thing that always increases. But now we're going to get to the deeper why. And it turns out entropy isn't some weird, mysterious force pushing things around. Nope. It's just a matter of pure, simple probability.
Let's go back to our box of gas, but to make it simple, let's just imagine there are only 6 little molecules inside. So, how many different ways can we arrange them? Well, there's only one single way for all 6 to be on the left side. But look at an even split, 3 on each side. It turns out there are 20 different ways to get that exact same outcome. We call each of these individual arrangements a microstate. And the big idea here is that nature considers every single one of these microstates to be equally likely.
And that right there is the key. Since there are just way more ways for the molecules to be in a messy, spread-out state than in a neat, ordered one, it is just overwhelmingly more probable that you're going to find them spread out. Now, let's scale that up from 6 molecules to a real amount of gas, which has something like 10 to the 23rd power molecules. The number of ways for them to be evenly split becomes so mind-bogglingly astronomically larger than the number of ways for them to be all on one side, that the odds of seeing them all on one side are, well, they're basically zero. The second law isn't a force, it's a statistical certainty. Systems don't want to be disordered, they just inevitably fall into the state that has the most possible arrangements. It's just playing the odds.
And this is it. This is one of the most important equations in all of physics. It's so important that it was literally engraved on Ludwig Boltzmann's tombstone. This is the bridge that connects the two worlds we've been talking about. S is the entropy we can measure in a lab. W is the number of those microscopic ways a state can be arranged, and K is just a number to make the units work out. This incredible equation tells us that what we experience as entropy is really just a measure of how many possibilities exist on a molecular level. More arrangements means higher entropy. It's that simple and that profound.
So, let's pull it all together. Entropy isn't just one simple idea. It is the very reason we experience time as a one-way arrow pointing from the past to the future. It's the fundamental roadblock that prevents us from ever building perfect machines and forces us to always deal with waste. It's the law that peels back the curtain and shows us that, at its deepest level, the universe runs on the cold, hard logic of statistics and probability. And it's the engine that drives every closed system, including our entire universe, on a relentless march towards its most probable state: maximum total disorder.
And that brings us to one final huge question. The second law of thermodynamics tells us that the entropy of the universe as a whole is constantly going up, always moving towards a state of greater and greater disorder. So, if that process just keeps going unchecked for billions and billions of years, what does that mean for the distant future? What happens when absolutely everything reaches a state of maximum uniform entropy? Well, that's a thought I'll leave you with.